If we're given a data set of x, y values, how do we get the best fit line? We can, of course, graph the data and sketch a straight line and take 2 points in that line and determine an equation. And we can usually, if we got a good eye, get pretty close to the best fit line. We try to get as close as possible in the average to the points. However, if we really want the very best fit, we probably had better go to derive and do it. Now there's a formula that can be used, and it isn't all that difficult to find the best fit line with calculator, pen, and paper, and so forth, but derive's a whole lot easier. So we take this data, and this is the syntax in which we put it in derive, and the regression line that we get is the best fit line. Okay, to get the regression line, in other words, we use the x mx plus b fit, and here's the syntax of that. X comma mx plus b in brackets. Again, we're telling derive that x is the variable and mx plus b is the form in which we're trying to put the data in this line. We get numbers for m and b. So we get an mx plus b function where m and b are just numbers when we approximate this fit command. The interpretation of the fit in the context of this problem, which is depth, flow rate versus depth, is that the y is the flow rate and x is the depth, so y equals mx plus b becomes flow rate equals m times depth plus b. As we saw before, we could plug in depth and immediately get flow rate. We can turn things around and solve for depth so that we could plug in flow rate and get depth. In order to do a power function fit, our derived syntax will be fit of x, ax to the p, and a data point. We have to specify different values of p. We can't leave p as a variable. Derive won't accept a parameter as an exponent in one of these commands. If the parameter's in an exponent, it won't do it. Anyhow, we can do this fit, we can plot the fit, and then by trial and error we can determine the p that works best. And of course we've done that in class and we've seen that. There is something in your class notes where I tell you how to use a vector function to do a lot of different fits all at once, so we don't have to do these one at a time. A polynomial model is typically this syntax, fit of x, ax to the n plus bx to the n minus 1 and so forth. Now we don't leave this as n and n minus 1. If we're doing a fifth degree polynomial, this would be ax to the fifth plus bx to the fourth and so forth on down to a number times x, or something, like let's see, it was fifth, it would be c to the x to the third plus dx to the second plus ex, and then plus an f on the end, plus a constant term on the end. And of course line number here as usual. Okay, a couple of cautions. First of all, n has to be less than the number of data points. If you've got 6 data points, don't try to fit a 7th degree polynomial to it, not even a 6th degree. 5th degree is the highest degree that you could fit. Polynomial of degree n minus 1 always exactly fits n data points, and it does that whether the polynomial is a good model or not. Polynomial often isn't a good model, so using really high degree polynomials is something we have to do with a lot of care. We've got to expect some kind of high degree polynomial fit or some approximation to a Taylor polynomial or something like that before we'd actually go to that much trouble to use a high degree polynomial. Usually third degree, maybe fourth, is about as high as we go, and usually we don't do that sort of thing unless we have a data set that has at least 2 or 3 times as many points as the polynomial, because the polynomial is going to wobble around, going to tend to wobble around to fit the data points, even if those data points contain errors. So what we usually look for good fit is a smooth curve that doesn't have any inappropriate wobbles, where we're chasing errors around and getting weird looking or inappropriate curves as a result.